Hi, Michael. Do you have any questions before we begin, Michael?
No, I do not. I'm good. Thank you.
Okay. You just wait a little bit more for more people to show up. Okay, let's get started. David is here. Jason is here. So let's get started then. Good morning, everybody. Does any one of you have any questions before we get started? If not, let's just begin then. Let me share my screen. This is not the screen that I want to share. Okay, let me see how I share this one. Can you see my screen?
Yes.
Okay, wonderful. Let's begin then. Today I'm going to continue on the second lecture on the quantum theory of light. So these are the topics that I'm going to cover, but I don't think I will cover all of them. So maybe you can get a gist for what quantum theory of light is and how interesting it is and how complicated it is as well. And maybe you can take this as a lifelong learning experience for you. So today we're going to talk about a quantum coherent state. The reason why we need to talk about a quantum coherent state is because we went through the exercise in the last lecture and found that if you look at just the quantum theory of oscillators, they don't make any physical sense. The idea we have there was that if you have an electromagnetic oscillation, such as that between a parallel plate as a cavity, and a parallel plate will have modes that looks like this, and then there will be the next higher order mode that looks like this and so on. So you can have higher and higher order modes. And if you were to stare at each of these modes, and if you look at them, you will find that the electric field just goes up and down. In fact, you can show that the electric field is of the form of an amplitude times a variation, KLZ something. Okay, so it has a sinusoidal dependence in the z direction, and in the t function, it is just a time harmonic oscillator. So E0t can be something like A0 cosine of omega t plus psi. And it depends on which mode you're looking at. Different modes will have different oscillation frequencies. And each of these is homomorphic or analogous to a pendulum. As I've shown here, the pendulum goes up and down. It will have sinusoidal behavior as a function of time. For the same token, the amplitude of the electromagnetic wave in the cavity also has this time dependence. Hence, we want to use the similarity of a pendulum and a mode to quantize the electromagnetic field or find the quantum nature of an electric field mode from the classical to the quantum. So we started out with a classical pendulum. We say that in a classical pendulum, then the Hamiltonian is given by this equation over here, where x is this thing that we have here. X is just this displacement in the x direction. And that would be the Hamiltonian for a classical pendulum. However, you can actually rewrite this in a more suggestive fashion so that it looks something more like a classical harmonic oscillator, something like p squared over 2m plus half m omega naught square x squared, where omega naught square is square kappa over m. Okay, so you can write a classical pendulum in this fashion, and then you can also make the p and x as a function of time. X is a function of time, and then derive the Hamiltonian equations. The Hamiltonian equations as an equation of motion for this pendulum. However, we want to do more than that. We want to derive a Schrodinger equation for the pendulum. That is, if you have a particle that is associated with a spring, if this particle is moving classically, it will just be sinusoidal. But if this particle is moving quantum mechanically, it has to be described by a wave function. The position of the particle is not deterministic anymore, but fuzzy. So instead, we have to convert this into something that looks like a wave equation. So we convert this into a equation that looks like this. And then we say that h hat is equal to p hat square over 2m plus kappa x square over 2. And then we say that p hat should be defined by an operator. It should be something looking like this. And if you use this definition, then this equation actually becomes something like a wave equation, very much like many equations that we have seen in this course. Okay, the p square becomes second derivative in x. And then the other term, which is this term over here, just becomes half m omega naught square x square psi xt. And then the right-hand side would just become minus I h bar partial t psi of xt. Okay, so it looks like a wave equation of some sort, which is called the Schrodinger equation. Sometimes it is also called the Schrodinger wave equation. And we have studied this equation by finding the modes of the system. And we say that it can be converted into an eigenmode equation by letting psi xt by using separation of variables. It can be written like this, okay? And if you plug this in, then the Schrodinger wave equation can be written as an eigenequation. And then the one that involves space derivative is this one. And then the second term will be something like this. And then right-hand side has a very simple time derivative. So it would just become h bar omega n psi sub nx. Okay, the space derivative operates on this, becomes something very simple. You just bring an I omega n down, and then when that is combined with I h bar, you give h bar omega on the right-hand side. And this equation can be solved in closed form. Okay, I would not belabor how we can solve this in closed form, but it can be solved in terms of Hermite Gaussian polynomials. And we can find all the energy levels And those Hermite Gaussian functions are the closed form solutions, denoting that psi of xt is psi nx e to the minus I omega nt. Each of this solution is called a photon number state. And each of these has an eigenvalue, which is h bar omega n plus half, I believe. Let me see. Omega naught n plus half. Okay, each of this has a eigenvalue that is given by this. Hence, this is called omega sub n. Okay, so the thing about this photon number states is that they look very oscillatory. If you plot this size of nx, it just might look something like this and then something like this. And it is all over the place. It is all over the place, meaning that if you were to go and interpret this wave function says that the position of the pendulum is uncertain, but for this photon number states, they are very, very uncertain. Okay, and there are many, many of them. The bizarre thing is that if you use the quantum interpretation of the expectation value of the position of the pendulum, which is given by this equation over here, the expectation value of the pendulum is given by the square of the wave function multiplied by the position variable, and then integrate. And this always come up to be 0 for all these modes that you have found, which are the photon number states. And you can also show that the expectation value of the momentum, which in this case would be given by the x minus I h bar partial x of this quantity over here, is also always equal to 0. So the expectation value of the momentum and the position are always 0. And in fact, x becomes a random variable in the quantum world. Okay, because x is uncertain. It can be any place on the real axis in this picture. And it cannot be described with certainty as to what the particle is. So that is not good. That is not good because the pendulum does not look at all like this. Hence, we have to find a way of connecting the classical pendulum with what we found in the quantum world. Okay, and so we have to look for the coherent state. Each of the states that we have found is just an oscillatory state. It's like a Fourier mode. It does not have a localized position. And what we need to do is actually to take these wave functions. Let me see, I have a picture of this wave function in the other slides. Say if I were to take this wave function and copy them back to this slide again, what I have is that these wave functions represent the particle being running all over the place and the position is highly uncertain. So what we need to do is actually to take a linear superposition of these photon number states and make them into wave packets so that the wave packet can describe more classically the movement of the pendulum. Okay, so let's see what we can do here. So in order to find the coherent state, we have to get the necessary tools, okay, or the math tools. And in order to find the necessary mathematical tools, then we need to revisit the Schrodinger equation again and find a different ways of representing it so that we can find the correct tools. Okay, quantum harmonic oscillator revisited. So I'm going to revisit this issue, which is to look at Schrodinger equation, which is something that looks like this. So if you look at Schrodinger equation by using the separation of variables, what you have is that you have that all the photon number states satisfy this equation. Okay, let me just put x here instead of size of nx, e psi of nx. Let me not put n. I want to find a different way of rewriting this Schrodinger equation to develop the necessary tools. And in order to do so, I would have to write this Schrodinger equation using normalized coordinate system. I have to define a new space coordinate, which is given by m omega naught over h bar x. Okay. And then if I were to do that, I find that this equation can be rewritten as half the square, the zeta square, c square, sorry, not zeta. And then this one is x squared. And after this change of variable becomes c squared. And then psi of c, I would just call this psi of c now because I've changed the variable to c. And then I take this h bar omega naught over to the other side and write this as e over h bar omega naught. Now Schrodinger equation becomes something that is dimensionless. Okay, and also the form of this suggests that maybe I can do some factorization. It turns out that if we were to look at this factorization, minus d c plus c, and then 1 over root 2 d c plus c. Okay, if you were to look at this factorization, this is very much motivated by the fact that this looks like minus a squared plus b squared. Because it looks like minus a squared plus b squared, maybe I can try a factorization that looks something like that. And if you do this factorization and multiply things together, things do not quite work out as you expected. So you will find that you get this term that you wanted. Okay, plus this c squared, but there's an extra term that looks like this because when you multiply these two terms together, they're altogether 4 terms. The extra terms comes out to be d c minus c, d c. Okay, so however, you can show that this extra term, when you operate it on any functions of c, okay, if you let it operate as a function of c, it always gives you back the function of c. I don't have time to demonstrate that, but it's just a simple application of chain rule, and you can show that this is the same as that always, and hence this new operator, you can think of it as differential operator, can be thought of to be the same as an identity operator. Okay, so this extra term that I have is actually something resembling an identity operator, and when it operates on function, it always gives back the function itself. Hence, I can write my Schrodinger equation in the normalized coordinate system plus c squared, okay, has been equal to this 2 factor that I was hoping to have. And then the first factor is d c plus c. And then the second factor is plus d c plus the identity operator, which just becomes half. Okay, this term here, I take it over to the other side of the equation, keep this part pretty much the same, and then just call this the identity operator, and hence it's been replaced by half. And I'm going to give new names to these operators. This thing I'm going to call the A dagger operator. And this operator, I'm going to just call it A hat operator. Hat means that they are operators. And the fact that I put a dagger sign there means that they are actually Hermitian conjugate of each other. I don't have time to prove that, but you can prove that quite easily, that these two operators are the Hermitian conjugate of each other. And if you do that, then you can actually write the Schrodinger equation more compactly using this identity. So you actually have this been equal to A dagger A plus half. Okay. And then you have this Schrodinger equation that I have previously. This term can be replaced by that term, and Schrodinger equation can be written as, let me see if I plug it back in, then I should have Schrodinger equation can be written as A dagger A plus half Cassini, psi of Cassini, which is this one, is equal to E over h bar omega naught psi of Cassini. So Schrodinger equation becomes very compact. And A dagger is called the creation operator. A dagger itself is called an annihilation operator. For obvious reasons that would be realized later on. But another thing that you find is that since these are operators, they're very much like matrix operators. They don't commute. They don't commute means that if you have A dagger minus A dagger A, they're not equal to each other. They actually are equal to the identity operator. Okay, you can show this quite easily by back substitution. And this is usually called a commutator, which means that A and A dagger do not commute with each other. And I would have now a succinct way of writing the Hamiltonian. The succinct way of writing the Hamiltonian is that is equal to h bar omega naught A dagger A plus half. Okay. And then Schrodinger equation then can be written as h dagger psi is equal to E over h bar omega naught psi. No, let me see if I can write it. I don't have to put the h omega there. And I can write it like this. And then I can actually now use what is called the direct notation. These are notations that are used, and you have to realize that h hat is just like a matrix operator. Okay, and this is the notation used by mathematicians where psi is a vector. And in linear algebra, we will have written something like this. H is a matrix. We usually put the double bar over it. Psi is a vector. We might write it like this. Okay. For the mathematician, they would just write it like this. But then for the physicists, they have their own notations. Okay. They like to call a vector a ket operator, a ket function. Okay. This is called a ket. And this actually is a vector. And it is actually equivalent to the vector psi written by the mathematician community. So both the vector written this way by the mathematician, the vector written this way by the linear algebra people, and the ket written this way are similar or homomorphic to each other. So it's like the Tower of Babel, and depending on which community you talk to, they have their own language that they're speaking about what the vector is. So let's now learn that in the physics community, a vector can also be denoted as such. Okay, so So if we have the things such as this one, then we have enough tools to actually derive the coherent state. Okay, and before I move further, I'd like to mention a little bit about the property of this annihilation and creation operator, which I don't have time to derive, but it can be derived by back substitution quite easily. Okay, so what you can show is that if I have a annihilation operator operating on the photon number state, that it will actually lower the state by 1. It becomes a photon number state with n less than 1 smaller. Okay, and then if I have the creation operator operating on the photon number state, it actually corresponds to producing a state with 1 photon that is larger. Okay, this is something that you have to assume to be correct at this point because I don't have time to prove them. And the photon number states are given to be here. Okay, so if you were to operate one of these photon number state with the creation operator, it will take you 1 state up. And if you were to operate on one of these states with the annihilation operator, it will take you 1 state down. Each of these photon number states has a physical meaning that it has n photons embedded in them. There's n h bar omega embedded in them. And as you elevate the energy level of these photon number states, you're making the eigenvalue or the eigenenergy to be higher and higher, and each one with the value of h bar omega. So there is a lot of things to digest here, and I don't have time to fully discuss them in the lecture, but just to let you know that the annihilation operator lowers the photon number state. The creation operator raises the photon number state. And what is more bizarre is that oftentimes when you read the physics literature, they are very terse. They will just denote this state with n. Okay, and then this equation would be something like this in the physics literature. And then the creation operator operating on the photon number state, which is just denoted by n here, would be just this one. Okay, so those are the terseness of the notation taken by the physics people, but you can always back translate that this means that, and that means that this is actually a vector, a mathematical vector. And then you can go backward, that saying that these vectors are actually functions in the coordinate space. They will look something like this. Okay, and then you can back translate them from very abstract terse notation to something more intuitive that you can see in the engineering world most of the time. Okay, so what is it about raising the classical equation to become an operator equation like this thing over here? What you have is that in the classical equations of motion for a pendulum, the motion and the position of the particle is highly deterministic. Its momentum is also highly deterministic. However, when you elevate the function to be a quantum function, the position becomes indeterminate. The momentum also becomes indeterminate. Actually, the position of the particle becomes fuzzy, and that fuzziness is expressed in terms of this wave function. Okay, the fuzziness is expressed in terms of that wave function, and then so if you have anything such as the momentum operator in a quantum way, in the quantum world, P becomes a random variable in the quantum world. Okay, if you have a position operator in the quantum world, in the quantum world, this x actually becomes a random variable. Okay, so in order for it to be a random variable, you cannot describe it with just one number alone. So you have to describe it like with a function of x, and this gives rise to fuzziness. the position of a particle actually becomes very fuzzy. And then in order to find the mean value of this position and momentum, you will have to find the expectation value. Okay, so expectation value of the position, which is the random variable, is usually regarded as x bar, which is the average value. And in order to find this expectation value in the quantum world, you find the quantum state that you are in, okay, and let them be found in this manner by taking expectation value. This is called the expectation value. Okay, so this random variable has a mean. The mean is given by this way. You can also find its variance. You can also find the variance of x, which is given by psi p hat minus p average square. And then you can actually work this out quite easily. And this would be the same as taking the expectation value of p hat square. You work this out by expanding, and then minus p bar square. So sorry, this is x. Okay, I'm putting x on the right hand side, so I should put x here. Okay, so this random variable has a mean and a variance. So in the quantum world, something that is deterministic becomes random. That's the first thing that you have to realize. So if you were to look at a quantum measurement, you find that electric field, which is something that is deterministic in the classical world, becomes random in the quantum world. So if you try to measure a pulse, an electromagnetic pulse, you find that in the lab, you'll find that the value of that pulse as a function of time is running all over the place because it is a quantum observable, which becomes a random variable. Another way of saying is that in the classical world, if you have a pendulum moving up and down, in the quantum world, that pendulum will not follow a perfect sinusoid, but it follows a sinusoidal function with some variance, some means and variance. The mean value might look like that you find in the classical world, but it can fluctuate about this mean value, which is something that you don't find in the classical description of the world. Okay, are there any questions so far regarding the difference between the quantum world and the classical world? The take-home message to say is that anything that you realize or are comfortable with to be deterministic can become a random variable in the quantum world. Okay. So let's look into the derivation of the coherent state. It was derived by Roy Glauber and Sudarshan around 1960s. But what essentially it amounts to is that if you look at the photon number states, and we have seen these photon number states before, they look like this. They are completely spread out. They don't look at all localized like what you see in the classical world. So what we actually need to do is to take a linear superposition of this photon number states, superpose them so that they become a wave packet. And if we superpose them so that they become a wave packet, then what you have then is what you see in the classical world as well. Okay, I will talk about this later on. But essentially, the gist of the story is that when you have something that is completely deterministic, if you denote this by a point in the quadrature space, this would be a perfect sinusoidal function. But because this is now a random variable, it actually has the mean and the standard deviation. So as you move this circle around, it actually maps out the amplitude not to be a perfect sinusoidal function, but a sinusoidal function with some kind of a deviation and the mean. And those are what we call quantum noise. The quantum noise can never be removed because they are part of nature. Okay, so in order to understand this, let's look at the coherent state, the derivation of the coherent state. A coherent state is defined to be the eigenstate of the annihilation operator. Okay, so if alpha is the eigenstate of the annihilation operator, after being operated upon, it will just be the scalar value. This is the scalar value times the eigenstate itself. That is the definition of what an eigenstate is. As we said before, you will find that this eigenstate is very interesting. If you can find this eigenstate, you can do quite a bit of interesting mathematics with it. I think that's how they get the insight. Say, let's look for a state that has this property. And then we can do a lot of nice mathematics with it. And as I said before, this coherent state has to be a linear superposition of the photon number states. Okay, let's assume that the photon number states are complete. And as I said before, photon number states are denoted like this. They are running all over the place. They have zero mean and quite bizarre values that don't have classical analog. But if you linear superpose them, you can make them to form a wave packet. So let's look at this coherent state. Because of the definition of what a coherent state is, that this has to be true. Okay, if I were to operate this with thing, and then if I operate on this summation, I would have just a hat alpha. Sorry, there should be an n here. Okay, I should have an n here, but the annihilation operator, as I said before, is an operator that would lower the photon number states, as I said before. I didn't prove this, but you can actually prove by back substitution. You plug in the wave function for the photon number states, and if you plug it in, you find that this is true, and it can be written more tersely in this manner. So what we have then is that if you have this case, then the photon number states as 0 will disappear actually when it's been operated by a hat, which is the annihilation operator. It will go to 0, and this summation now can start from n is equal to 1 to infinity, and then you will have Cn. And then using the property of the annihilation operator, this can be written as this. Okay, it gets lowered by 1. The summation now goes from n equal to 1 to infinity because n is equal to 0 state does not exist anymore. It has been annihilated by the annihilation operator. And then I can resum this thing so that it starts from 0 again, okay, by a change of variable. Okay, I can always do n prime equal to n plus 1 kind of thing to do a change of variable. Then the summation now again goes from n is equal to 0 to infinity. Okay, so I have this thing, and I like to find out what these coefficients are. And in order to find those coefficients, I just use the completeness of Fourier series, and that I look for the right-hand side already. Let me look at what I look for the left-hand side already. Let me look at what the right-hand side should be. And now if I substitute in the right-hand side, put this into the right-hand side, I should have this being equal to alpha, n is equal to 0 to infinity, Cn n, okay? So I have this series which comes from the left-hand side should be equal to this series which comes from the right-hand side. And assuming that this is very much like Fourier series, you probably learn in your undergraduate course that if two Fourier series are equal, And if they're complete and orthogonal, these are orthonormal bases. You can show that quite easily, that these coefficients must be the same. The coefficient of these two series are the same. And so I can actually, let me see, there is a way of removing all these things. So I immediately now conclude that Cn plus 1 must be alpha Cn divided by n minus 1. So this equation is just obtained by equating these two coefficients, okay? And if I equate the two coefficients, I have this thing. And now I can solve this equation recursively. I can start with 0, find C1, and have C1, and find C2, C2, and find C3. And so if I solve this equation recursively, then I find that Cn is equal to Cn minus 1 alpha. And then I keep working this recursively, then alpha square n minus 1. And then it goes recursively until it goes to the beginning of the recursion. It arrives at C0 alpha n over square root of n factorial. Okay, you can solve this recursively, and hence you can find Cn. Cn can be expressed in terms of C0. And hence the coherent state can be written as C0. N is equal to 0 to infinity. And then I plug this into the definition of the coherent state, which is what I have over here. Then I would have alpha n over square root of n factorial n. Okay, so I have found a coherent state as a linear superposition of the photon number state. So this is coherent state. And the right-hand side is photon number state. The photon number states are non-classical states and not physical, and they're not very good to work with. So I have to find something more physical, which is actually a wave packet that you will see later on. And furthermore, I have to have the normalization condition that any state vectors that you have in quantum theory has to be normalizable to 1 because of the probabilistic interpretation of a quantum state. Okay, this follows from the probabilistic interpretation of a state vector. So actually there are lots of things to digest here. Okay, you have to learn about probabilistic interpretation and so on. So you can actually find C naught using this normalization condition. And if you plug that in, and further using the fact that this photon number states are orthonormal. Okay, if you plug it in using the fact that the photon number states are orthonormal, that they're given by this Kronecker delta function, you can find that C naught square e to the minus or plus alpha square has to be 1. And finally, you find the coherent state to be equal to e to the minus alpha square over 2, linear superposition of the photon number states. Okay, linear superposition of the photon number states. Okay, and let's prove to you that this, in fact, is the wave packet that you're looking for. Okay, and we will show that when this thing time evolves, it actually evolves like a quantum pendulum. Okay, so when something time evolves, it actually evolves like a quantum pendulum. And in order to find the time evolution of this, we have to plug this coherent state back into the Schrodinger equation. Schrodinger equation says that the Hamiltonian times a quantum state has to satisfy this equation. Okay, in other words, that you can solve this equation in closed form, and that psi of t is equal to e to the minus I h hat t over h bar psi of 0. Okay, you can actually solve this equation quite easily if h is time independent. Okay, so this is something that you have to learn a little bit more, which is that what is the meaning of the exponentiation of an operator? Exponentiation of an operator has meaning only if this operator, like if I write it in this manner, exponential to an operator has meaning only if it acts on an eigenvalue or eigenvector of A. Okay, you can show that this actually is the same as this. If V is an eigenvector of A. If you can show that this is true, you can actually expand this into a power series. The left-hand side is just 1 plus A dot A over 2. I think I'm correct, yeah. Sorry, this first term is just A. Second term is A dot A over 2 factorial. The third term is A cubed over 3 factorial. You can do this, and if it operates on a vector that is an eigenvector of A, then this thing simplifies. It will simplify to something like this, okay? So what happens is that if this is actually an operator, but if it operates on a state that is a quantum state or eigenvector state, for instance, if you have minus h hat t over h bar operating on a photon number state, it will produce a time evolution that is very simple. That time evolution is just I omega n t, n. Okay, because you can find that the eigenvalue of this eigenvector is just omega n, which is n plus half omega naught. Okay, those are a lot of mathematical details that I don't have time to get into, but you can find the time evolution of this quantum state in closed form, because you can find the time evolution of each of these photon number states. Okay, so if you were to do that, you find that this coherent state can evolve as a function of time, and that I don't believe I have time to go into. So if you can time evolve this coherent state, you find that the coherent state actually behaves like a, so the coherent state as a function of time would become something like something that depends on time out there, and then having a coherent state where the complex number is a function of time as well. Okay, you can find that this is true. A time evolution of a coherent state behaves in this manner, and that you also find that the annihilation operator, when operating on this coherent state, would just give you a complex number, okay, times that coherent state, where this complex number is actually now, let me see.
Hello.
Yeah. Yeah, who is that, please? Hello?
Sorry, Professor. It's okay.
Am I okay?
Yes, it's fine.
Okay. Are you getting the images and the transmissions okay?
Yes, it's fine.
Okay. Sorry about that then. So if you can find this thing, you will find that this coherent state behaves in this manner, where alpha tilde It's a complex number. There's just alpha e to the minus I omega naught t. Okay, so you can actually go through this kind of mathematics very nicely. I don't have time to show in detail. That is, now if you look at the coherent state, how it involves or how it evolves with time is that it just looks like a quantum pendulum. Okay, it is a wave packet that moves back and forth. And that would resemble the time evolution of a pendulum. And now you can see the connection between a quantum state and the classical world. So if you plot this in this seismic plot, you can find that the coherent state actually behaves like that. Okay, and I don't have time to talk about the rest. Okay, but they are written in the lecture notes. The message to take home here in this lecture is that in order to connect the quantum pendulum with a classical pendulum, you actually have to look at the coherent state. And the coherent state says that you will see something that looks like a pendulum now, but the wave packet has a mean and a standard deviation, which means that there's still some randomness associated with this coherent state. The position of this pendulum is not 100% certain. It has some fuzziness. And if you were to plot this quantum pendulum out, you'll find that it has some fuzziness about its position. Okay, that is the take-home message about this coherent state. I guess I will stop here and ask if you have any questions. Does anybody have any questions? Okay, if you don't have questions, then I will give a review this Friday before I give the final take-home exam. Okay, I'll let you go if you don't have any questions. Thank you for coming. I know this.
Okay.
Yes, you have a question?
Yeah, it seems this stuff is kind of tough to me.
What is tough to you?
I mean, today's lecture seems a little bit tough to me.
Okay. I will give you the lecture notes and you can read the lecture notes. And if it is not understandable, you can communicate with me by email. I know it's difficult because it has a lot of materials in it, a lot of concepts. And those concepts are not easily digestible. Okay? But it is the direction you have to go if you want to understand the quantum theory of light.
Okay, thank you, Professor.
Okay, thank you for coming.